pretty,
indoors. The better thing.
yeah, that's good to be safe. Good to be safe. Yeah, lots of things are happening nowadays, and you better stay home with all this gas prices and stuff. Oh. Anyways, let's recall what we did last time and see what else we can add to this story. So we had been working with so-called various conditional probabilities. And yes, hi, I'm glad that it looks like you're still remembering about the class, and that's very impressive. Otherwise, everybody forgets. That's definitely no good. So let me try another little exercise that will be, I guess, showing us some stuff. Oh, here's a picture. Let's try to do problem with picture. Problem number 16. In this exercise, I have two separate valves, P and Q. And we need to have a water for emergency nuclear reactor. Oh, that's important. If it's important as an emergency, we need to better make sure it works well. That's why they have those valves. So backup. Q is probably backup for making sure everything works. So anyways, they give us a probability of opening. So in exercise 16, we have probability that something is going to be opened, not the reactor or the valve, and this is 9968, pretty high chance, which is good, but it's still not 100%. In fact, probability is never 100%. So there is always 99 point something, but good things happen. So they looks like have the backup sensor. And the question is, find the probability when both of them are working. So both means and P and Q. I say, where's P and Q? Well, they decided to call them as P and Q, and we saw last time that and, so when both working means one and the other works, so it's 9968 times another 9968. So and means times, and that's what I have here. So we multiply them together like that. And means times. Well, looks like what I need is to just multiply, and that's the idea, and that's what we learn in this section. In fact, if you check and see the name of this section, where's the name of the section? Does it say? Oh, here it is. Multiplication rule. So it wants you to multiply, basically, and that's what you do in pretty much every exercise. So let us multiply. So I'm gonna get my favorite scientific calculator, right? Scientific calculator, and put in the 9968 and times it by 9968. Some people say, Alex, why don't you square it like that? Yeah, I can square it or multiply it with itself twice if you're not sure. To be sure is good idea, right? But the point of story, you have this probability, they both are open. And again, it's pretty good probability level, so it's fine with us. So one and the other, they work, and that's how we do this. So and means times. It turns out this whole procedure is not being abandoned in the next section, because next section continues the same story, because it again is called multiplication rules, and it uses more of this so-called conditional probability part, and it actually provides us with a pretty specific kind of exercise. So these specific type of exercises are, I think, nicely described in the problem 15. Because the specific is all problems has the same thing, at least one, at least one, at least one. So what are they really talking about? Well, the student in exercise 15 wants not to miss the test. So looks like in exercise number 15, the student uses alarm clock. The alarm clock that has probability to work 99%. 99% the chance that student wakes up and takes the test, but 1% it's not going to happen. Remember, we used to call it as with a bar. Not working alarm clock means it's 1 minus probability that it's working. Or one can intuitively say, if you subtract 99% from 100%, then it will be a 1% chance that alarm fails, 0.01. Complement, right? We used to call it as complement in statistics. So it says that 0, 1, or that's 9, or what kind of number did you put? Maybe I better write it careful. So it is actually 0.01, 1%. So working, not working. So student wants to make sure that not gonna go for that bad situation, 1% chance. So buys more alarm clocks, decides to use 3 alarm clocks to wake up the whole building. I guess it's gonna be and one and the other and the third. So the question is, what's the probability that the student makes it to the exam? At least one works. At least one works. So I can show you the way that we should not do the problem. Actually, let me do it the nice way, and then I'll show you the way that we should not do it. So I'll do the problem 2 ways. So one way is to use the complement. So it turns out the complement to at least one works will be all of them fail. All fail. The opposite will be, well, something is not failing. We say all of them not failing. Well, if all of them fail, if at least one is working, that's good enough student goes to the exam. Maybe just one worked, but the other 2 alarm clocks did not, or all of them did not work. See, that's the opposite to at least one to work. That's worth to think about. And I will go over this as I'll do the problem second time. So let me just find the probability that all fail. So that's pretty sad, right? All of them failed. Student had 3 alarm clocks and they all failed. So student did not come to the exam. Pretty bad idea. So it means that first one did not work and times second did not work, right? And times the third one. So all 3 alarm clocks failed the whole thing, and looks like it will be 0.01, right? Which I multiply with another 0.01 and with another 0.01, and this will be 1 millionth, or I can just let calculator do it. So it's 0.01 cubed. And then I will be subtracting it from 1 because I want to find the opposite, right? Not all of them fail, but at least one did not fail or more. It's fine. And okay, it's calculator. So it looks like 1 subtract 0.01 to the power of 3. And notice it's 99,999. So it's very high chance that student will make it to the test. 99,99. That's definitely we say the student is going to make it. But somebody else can say, Alex, maybe still 1 millionth chance that it's not going to happen. Yeah, but 1 millionth chance we say is not possible. That's the way the whole thing is set up. So if it is actually less than 1% chance, it's not going to happen. That's how we assume that. So anyways, some people might say, Alex, I would do this problem, I would approach doing it differently. So they want at least one to work. So I could just say probability that one works and the other works and the other works. So that's what we're trying to find. Well, I would say not really. So if probability that one works is 99% and the other works is also 99 and the third is 99, that will be 99 cubed, right? I can put it in the calculator, find it later. But this is not just the case because it could be when first worked and second worked, but the third alarm did not. And student still has woken up and still made it to the exam, but one alarm clock is still no good. But it doesn't really matter because they want to at least one to work, you see? So not all of them, but at least one. So it means that two first worked, or it could be the first that worked and a third that worked, but the middle did not work. See how many different possibilities we'll have to consider if two of them worked. So it could be the last two worked, but the first one didn't work. So I just try to show you all the cases when my two alarm clock worked, first two or first and last or last two, and they all gonna give you the same exact product, like 99% for first to work and 99% for second to work, but for the third, 1%. Or here you have 99% and then 0.1% for the middle one, right? Not to work, and then 99. So please notice that these are the same products because we just commute numbers. So I put 0.01 in the middle, or I can put 0.01 in the first position. But in my multiplication, I'm going to have same three products. So 3 multiplied by 0.99 and then by 0.0. So 3, exactly the same things we have to also consider together with that one. So that's when two alarm clocks worked and one did not. But there could be only one that worked. Let's say first one worked, so he bought some alarm clocks and one only works and the others fail. And that's pretty sad, but it's fine because he still wakes up and goes to the test. So the one that worked could be, again, the first one or the second one or the third one. And the other two did not work. You see, that's kind of similar to the previous, right? And that's what you need to consider if you calculate this directly. If you were to find all the at least one cases listed. And that's why I don't really recommend you to do this because that's a lot, right? It's much easier to approach it from the complement to say one minus. So the case that all failed, the opposite will be at least one did not, and that's it. So opposite to means complement, which is one minus, and that's what we just calculated. And that was the nice number. Was it? Did I write it down? I didn't write it down. Yeah, I did here. So it's 99999. So the point of story is now I'm gonna produce the same exact 9999 when I add all of the possibilities in here. So here were 299, so it's squared, and here's 199, so that one will be squared. So three cases when one works could be first one, middle one, or the last one. Three cases when two of them work, so the last one may not work, middle one, or the first one. It's kind of dual. And one case when all of them worked. So if I decide to add them all together, I better get the same exact answer. The reason is in mathematics, the answer is always the same, right? So then it's correct. If it's not the same, then it's not correct. One of them not correct. So let's try 0.99. I want to cube and then add it. You see how much work we need to do if we calculate it from direct approach. And that's definitely a little bit too much and easy to get mixed up. So advice is always try to do it shorter way so you don't have a chance to mix up when you are doing your calculation, especially on the exam, right? And right now I'm just enjoying the process, but look at this. I better get exactly the same answer and say it doesn't give you the same exact answer. Well, probably because I did not enter something here. I need to put square. So notice this is exactly 9999. So approaching it directly, which is taking, I don't want to use word forever, but a long time compared to the approach from the, I guess, opposite from the complement way give us the same result. So to me, it doesn't matter. As long as you do it right, perfect. But definitely will show you how to do it with the complement. And that's what the textbook also does. And that's the way to go. So let's do another exercise to make sure that everybody agrees that we have pretty much standard process to do all problems in this section, use the complement. So let's say, what's the probability? Let's say exercise number 9. Or if you have a feeling to do some other exercise, we can definitely do it. And say, Alex, I just was on a vacation. I have a feeling to rest. Well, I guess after I do this exercise, I will let you rest. You deserve it. I know that you worked hard, and I'm pretty happy with your results. So everybody's getting good results, and that's the way to go. So that's the way to get to the end of semester. We have another, like 6 weeks or so left. So we'll just keep working on statistics. So in exercise number 9, I will say at least one traffic violations. And somebody decides to run the red traffic light because the probability that there be a ticket is 1%. No, 10%. Well, which is actually 0.1, 10%, which is actually kind of high, but still you may not get it. Well, what if you do it 5 times? What the chances will be if you do it 5 times, and the equation is probability of getting at least one. Remember, just like with alarm clocks. At least one means it could be one, could be two, could be three, could be all of them, right? But at least one, that's what they care about right now. So since it's standard approach from the opposite, 1 minus probability that none of them work, because to calculate probability that none of them is not as hard, but at least one will take as a standard process with one, with two, with three, so that's a lot. So I will go with probability that none of them worked, so you got lucky 5 times in a row. So probability that you got no violation on the first time and means times no violation on the second time and means times on the third and so forth. All 5 times, no violation. So what does that give us? 5 times. Well, I need to know was the no violation actually equal to, and then multiply it with itself for 5 times. So I go with the complement formula, right? It's always same thing. So subtract from 1 probability of violation. So from 1, I need to subtract 0.1 and end up with 0.9. So there'll be 0.9 here, 9 here, here, dot, dot, 5 times 0.9. So this is 0.9 to the power of 5. So notice I don't want to multiply 0.9 with itself for 5 times. What for? Because I'll just need to subtract it from 1 anyways. So I'll let calculator to do that work. Because otherwise, if you start to mess with all these decimals, there is a chance that you might get it miscopied, right? It happens to me as well. So you want to minimize that chance. So you just let calculator take care of it, because definitely nobody will do this problem by hand. So you want to always use a calculator for this type of exercise. So subtraction 1.9. So you need to have a good working calculator. And I recommend you to use this Desmos, right? Desmos called. So scientific calculator, free, absolutely free. And that's a good thing about it. So it is equal to 409. So you get already about 41%, right? Chance that you will get a traffic violation ticket by mail if you run this red light 5 times. Because sometimes people say, oh, I just ran the red light and never got the ticket, so I'll do it again. Well, bad idea, because if you do it a few more times, the chances from 10% increase to more than 40%. And that's a good chance. So it looks like you will get eventually the ticket. So think about it, right? Anyways, so the process of at least one is always the same. From 1, you subtract probability of none of them. So what else is in this section? Let me try Titanic exercise, and then I guess I'll let you go so you can enjoy the rest of the day. And thank you so much for remembering about coming over. That's very impressive. So I'm gonna maybe clean this mess. Stop share it again. And try to do exercise number 19. Titanic exercise. It says, find probability of a man given that person died. What are they talking about? Well, they're talking about the part of the sample. They're no longer considering anything else, but they're given only this portion. So they don't care about who survived. They just, in this particular equation, given that we're dealing only with that part of the sample. Okay, so what's the total? Remember, probability is always a fraction. So this is a fraction that has denominator that totals everything. So 1360, 104, and so forth. So this is total that I put on the bottom. And then for the top, I need to have only what I need, and they cared about probability that it was a man, so 1360 men, there'll be in here. And that's what I have to calculate. Okay, so let's calculate. So when something is given, it's always a part of sample that we care about, and then we'll produce the answer. So 1360, and then I divide this by the sum of 1360 plus 104, and then plus 35, and finally plus 18. So this is the result, and this is going to be about 89%. So you just put a few digits. It doesn't take too long, because some people say, Alex, it's 90%. Well, it is really a little bit less than 90, so it takes a second, probably 2 seconds, to put this extra digits. So that way you have a nice answer. So they usually put at least 4. But you say, Alex, what if I do 90%? I love to round. Okay, I will accept it, no problem. I'll just put a minus. I'll say, okay, you didn't get A, you got A minus, but it's still an A. We don't have A minus grade in our college. Even if I want, I cannot put it in the system. It's either A or B. But just to realize this is actually not 90%. That's what I'm trying to say. It's a little less. So maybe I'll do one more and then I'll let you go. Maybe one more. This is the last push. How about one more? How about number 22? Let's do the last one. So again, in a man or a woman, given that selected someone who died. Oh, that's analogous kind of exercise, right? So we are given that same exact condition that we are dealing only with the second row, but now it's changed. It's either man or a woman. And again, it's given that somebody has died. It's pretty sad, but let's calculate it. So it looks like now we need to get the same denominator, because that's where we concentrating at. So 1360 plus 104 plus 35 and plus 18. So this is denominator. And for numerator, we have now a little bit more. We have or 1360, or, so I need to plus, right? Or means plus, and means times, or is always plus. So we add those two. So pretty much the same thing. And where's my favorite calculator? So when you say, Alex, why don't you just add it so you don't have to re-enter all of these numbers? Just put plus 104 on the top, and that will be your answer. And you say, well, okay, looks like it's 96 something. Okay, so whatever the answer is, I'll just put down a few digits and then be good enough. So conditional probability when you shrink your sample. I know it's a lot to get after the spring break after you enjoyed it, so enjoy it more. So we'll get there again on Wednesday. Thank you so much for coming over. If you have any questions, please let me know. If you want to talk something with me, please do that. Again, grades are all I posted on the Brightspace. If you cannot see them or something else happened, well, just ask me in person on Zoom. Put the question in the chat, or just wait for other students to log out so we can talk about the grade and I can help you and give you an idea if you want to raise your grade. If you're already fine with your grade, that's super good. Just keep up doing great job, whatever you did before. Don't stop. Just do not stop, please. Okay? So I'm gonna stop recording. And if you don't have questions at the moment, email me questions.